how could you not be excited about something as monumental as this?
In just a few weeks, NASA's Europa Clipper spacecraft will launch on a journey to a mysterious moon of Jupiter. We're here today to talk about why we're going to this moon Europa and the final preparations to get the spacecraft to the launch pad. I'm Jari Cook. Welcome to NASA's Jet Propulsion Laboratory. We're here live to talk about Europa Clipper today. I'm joined by members of the Europa Clipper mission team. Some of them here with me at JPL and some of them coming in remotely. They're here to take your questions about the Europa Clipper mission today. So I'm going to introduce some of our panelists. We're going to start with NASA Planetary Science Division Acting Director, Gina DiBraccio.
Hi, everyone.
We also have Europa Clipper Project Manager, Jordan Evans. Launch Services Program Senior Mission Manager, Armando Piloto. Propulsion Module Delivery Manager, Stuart Hill. And Deputy Project Scientist, Bonnie Barati. For anyone watching who'd like to ask a question, you can use the hashtag AskNASA on social media. Our phone lines are also open to the media, and if you want to ask a question and get in the queue, you can press *1. To start, I'd like to welcome JPL Director Lori Leshin to make some opening remarks.
Thanks, Jari. Good morning, everyone, and thank you for joining us. The Europa Clipper team has been working incredibly hard, and our journey of exploration and discovery is about to begin. This is an incredibly impressive mission, and you're going to hear today from the experts who are going to give you an insider view of how we've gotten here and about the science to come. But let me just say, this is an incredibly impressive mission and team. As you heard in the video, it is the largest interplanetary spacecraft ever built by NASA, and one of the biggest things we've ever assembled here in our clean room at JPL. It's been an extraordinary journey just to get to this point. And really, the excitement is just beginning because the science lies ahead. And we have 10 science investigations that are designed to examine Europa, this incredible icy ocean moon, from every different perspective and to give us great insights into whether this could be a habitable world. I want to just take a moment to congratulate our incredible team. Over 4,000 people have worked on Europa Clipper since its inception, since it was sort of formally approved about a decade ago. And those include our team, of course, here at JPL, our incredible partners at the Johns Hopkins Applied Physics Laboratory, incredibly grateful for that partnership, as well as our colleagues across NASA at Goddard, at Kennedy, at Marshall, at headquarters, all of the folks that have supported us to get to where we sit today, just a few weeks from launch, a few weeks from the opening of Europa Clipper's launch period. We're incredibly grateful for that partnership, for that collaboration. We're incredibly proud of the work that this team has done. And just know, they won't tout their own horn, so I will. They have been working literally round the clock in some cases to make sure Europa Clipper is just right and ready for launch. And I'm excited for you to hear the progress there. As I close, I will say I often talk about these missions as modern cathedrals. They are generational quests. We scientists have been dreaming about a mission like Europa Clipper for more than 20 years. We've been working to build it for 10 years. It's going to be another 10 years because Jupiter's so far away until we have all the science in the bag. And so it really is a very long-term investment and quest. And I'm really proud that as humanity that we choose to undertake these difficult and long-term goals, things like exploring the unknown out at Jupiter. So go Europa Clipper, and back to you, Jari.
Okay, thank you, Dr. Leshin. Okay, I'm going to hand it over to Dr. DiBraccio.
All right. So it's great to be here today talking about the Clipper mission. And let me just start off by saying that NASA is so excited to be one step closer to answering fundamental questions about the solar system and beyond with Europa Clipper. Now, Clipper and this mission is really a crucial part of NASA's planetary program. Within our solar system, we have the opportunity to really explore a diverse set of planets and planetary bodies. So as an ocean world, Europa is very intriguing. And this mission is going to help us to understand a complex piece of our solar system. Now, looking at NASA's planetary fleet chart that you see here on the screen, this demonstrates the diversity of our program. You can look across the missions that we have that are currently in development and operating in space right now. So the inner swirl that you see on this chart, this is showing the missions that we have at the Moon and Mars, and then the outer swirl focuses on the rest of the solar system, showing where our missions are based on their location. And these missions, they vary in scope. So we have our small focused investigations, but then we also have our large strategic missions, and these are the ones that are of national importance. Now, Clipper, which you can see that's highlighted in the bottom left of this chart, that's one of those large strategic missions. That's a NASA flagship mission. And the science goals of Clipper are based on recommendations, not just from NASA, but the greater science community. So Clipper and the science that it's going to achieve, this has been a decadal priority. It's been a priority across the decades, but also for decades to come, just as Laurie was saying. So one of the reasons that Clipper is such a high priority is because we have the opportunity to go to a new place that we've never explored before in depth. Within our planetary fleet chart that you see here, we've explored the gas giants planets in the outer solar system. We've explored the rockier terrestrial planets as well in the inner solar system, and we have exciting missions that are currently visiting asteroids and other small bodies. But now we finally have this dedicated mission that will go to explore an ocean world in depth. And this is really an important part of our solar system and beyond, because we think that ocean worlds might actually be a common type of world outside of our solar system. So as we move to our next image here of Europa, we can see that it has some of these amazing features on its icy crust. And scientists believe that Europa is one of the most promising places to look for life beyond Earth. And so just to be clear here, Clipper is not actually going to look for life itself, but it's going to characterize the habitability of Europa. And to do this, we have a powerful suite of instruments that you'll hear about in just a little bit from some of our other panel members. But some things that Clipper will actually do to assess the habitability of Europa includes characterizing the subsurface ocean. We're going to determine things like the salinity of this ocean and just how deep it actually is. We want to investigate the structure of the ice crust that's overlying this ocean and search for the existence of subsurface lakes as well. And then finally, we're really looking to understand the materials that make up Europa. We want to understand the composition of the strange reddish-brown material that you see on the surface here in this image, but also other parts of Europa as well. And so, given everything that we've really learned about necessary conditions for life, Clipper is going to tell us if Europa has all of these ingredients for life. So what we learn with Clipper and the habitability of Europa, this is going to pave the way for the future, for future missions to Europa and elsewhere in our solar system where we can search more directly for life. So Clipper is going to be the first in-depth mission that will allow us to characterize habitability on what could be the most common type of inhabited world in our universe. So before I pass it on to our next speaker, what I'd like to do is just take a moment to talk about what I'm most looking forward to. And it's really hard to pick just one thing. So I'd like to focus on both the people and the science here. As Laurie was saying, our team has been working so hard, not only over the past many, many years, but especially over these last few months. I've been watching them really push to get to the finish line here with launch. And so I'm really looking forward to experiencing the launch with everybody in just some short time here. But also as a scientist, I'm really looking forward to the data. I can't wait to see these high resolution images once we make it to Europa to really see what the surface is like. And as somebody with magnetometer experience, I'm really excited to look at the magnetic field data to understand how we're characterizing that subsurface ocean of Europa. So with that, I'm going to turn it over to Jordan Evans, who is the Europa Clipper project manager.
Thank you very much, Dr. DiRocchio. I'm excited to say that we are headed to the launch pad and ready to fly Europa Clipper's mission at Jupiter. I'd like to start with a little bit of current status. The Europa Clipper project has gotten the green light from headquarters to prepare for the launch pad. We've recently completed all of the closeouts that we had planned prior to the start of fueling. If you could please bring up my first photo showing the latest spacecraft configuration. This was taken last week, just prior to moving the propellant loading scaffold over there on the right into place and connecting the lines to start fueling Europa Clipper's internal fuel tanks. We're on track for our launch period that, as was mentioned, opens October 10th. And this week, we're continuing to load the propellant into the spacecraft. And then we'll do a few days of final closeouts where we install our install before flight items, remove the red tag, remove before flight items. And we're quickly approaching the start of what we call joint operations, where the Europa Clipper team and the SpaceX launch vehicle team come together and start their integrated activities. You'll hear more from Armando about NASA's Launch Services Program activities and the amazing team that they've assembled for Europa Clipper. After nearly 1,000 days of assembly, test, and launch operations, or ATLO as we call it, because we like acronyms, the work we've accomplished ensures that we're ready for launch. In that time, the team has been busy with the careful and methodical assembly of the spacecraft at JPL after receiving key pieces of hardware from the Applied Physics Lab and the science instruments from JPL, APL, and our 4 additional institutions involved. There's been extensive testing at JPL, at APL, and also at NASA Goddard. If you could please bring up my short video about testing. We've taken Europa Clipper into a vacuum chamber to simulate the cold vacuum of space to ensure the spacecraft can maintain temperature and function over that hot and cold portions of the mission. We did vibration and acoustic testing to shake the spacecraft like it will experience on the Falcon Heavy rocket and blast it with the rocket noise that it'll experience inside the Falcon Heavy fairing. We tested the hardware and software together in system tests, tricking Europa Clipper into thinking that it's flying. And from launch all the way through flybys of Europa, we tested it in the presence of problems. We pulled wires out to see that the internal fault protection would recognize that and be able to switch to backup communications lines. We also did extensive analysis and testing of electronics and circuits under the conditions at Jupiter, including a full suite of electromagnetic compatibility testing to ensure that all of the instruments can operate together with each precious flyby of Europa. One of the major milestones we've successfully passed at the Cape is the installation of Europa Clipper's massive solar arrays and the Reason radar antennas. You see on the model here on the side, there's 3 Reason antennas, radar antennas connected to the solar arrays. They came together for the first time at the Cape, and they were tested not only with each other, but also with the Reason electronics that are inside a radiation vault just below our very large high-gain antenna. While launch may seem like the beginning of the mission to many, the Europa Clipper team has been solving some very tough engineering challenges to get to this point. Doing the first in-depth study of the moon, Europa, is extremely difficult. If you can please bring up the trajectory video. One big challenge is just getting to Jupiter, and we do that with what we call a mega trajectory, a Mars-Earth gravity assist. We steal a little bit of angular momentum from Mars and Earth, and then even with that, it still takes 5.5 years to get to Jupiter. And then during that time, we travel a distance of 1.8 billion miles. Once we arrive, the science tour and trajectory design is equally as challenging. If you've heard of the 3-body problem that's been popularized by a recent TV show, Jupiter is essentially a 7-body problem. You've got Jupiter, the Sun, the Europa Clipper spacecraft, and the 4 Galilean moons. Our orbital trajectory lead says that there's no other place in the solar system that is so dynamically complex in terms of gravity. Our mission does flybys of Europa, but is actually in orbit around Jupiter. And so for the primary mission, we do 49 flybys, but in the end, we end up orbiting Jupiter 80 times. And to be clear, we're not landing on Europa, making no attempt to land there. We do get as close as 25 kilometers above the surface. That's about 16 miles. And these flybys cover both hemispheres of the moon and a variety of latitudes to get us near global coverage of the moon for the science instruments. Another challenge is having a solar-powered mission at Jupiter. We had to build these giant solar panels to capture the small amount of sunlight at Jupiter to power the spacecraft. And that's led us to having the largest planetary spacecraft for NASA ever. You'll hear more about the massive solar arrays from Stuart Hill a little bit later. I think the most significant challenge that we've had to deal with on Europa Clipper is radiation. If you can please bring up the animation showing Jupiter's radiation environment. This is an artist's rendition of the magnetic field and the intense radiation environment. You can't really see the magnetic field lines as they're shown here, but it helps give you a sense of that radiation, that trapped environment where Europa and the 3 other Galilean moons orbit. That radiation environment is created by this magnetic field that is 20,000 times more powerful than Earth's magnetic field. And that field spins and accelerates and captures particles, basically creating a giant particle accelerator that the Europa Clipper spacecraft has to fly through with each of these science flybys. So we designed a science tour that dips in and out of this most hazardous radiation environment close to Europa. We fly in, we get the science data we need, we fly out, process the data, send it back to Earth, and then go back for another flyby where, again, the spacecraft bathes in that radiation environment. And each of those flybys, the surface of the spacecraft is exposed to the equivalent of a few million chest X-rays. And yet, the Europa Clipper instruments have to be sensitive enough to gather the critical information that scientists need to learn about the moon. So as we look forward to launch day, I'd like to share some thoughts about launch. On launch day, we'll have our test team that has assembled the Europa Clipper stationed at Kennedy Space Center. They'll get the spacecraft into the proper power configuration. They'll let me know the spacecraft is ready to go, so I can let launch services know that as well. And then in parallel, we have a combined JPL-APL Goddard team that'll be in mission control here at JPL, keeping a close eye on the spacecraft and making sure that it works as it's supposed to once it's off the rocket. If you could please bring up the fifth image, the artist concept of Europa Clipper in space. I can say the excitement is building with each passing day, and the thing that I'm most looking forward to is getting through launch and deployment of the solar arrays. As project manager, my primary responsibility is managing the risk of this mission. And that deployment of the solar arrays, the separation from the spacecraft, that all happens about 3.5 hours after launch, and is the moment when we will have retired a tremendous amount of risk on this mission. And we will begin our 1.8 billion mile journey to perform the science that this mission was designed to do. At this point, I'd like to hand it over to my dear friend Armando Piloto to talk more about the road to launch.
Thank you, Jordan. I am a senior mission manager for the launch service program here at Kennedy, and we are responsible for managing the launch service provided by SpaceX. I'll say up front that we plan to give Europa Clipper a powerful ride into space, and we are on track for launch. Europa Clipper will fly on a Falcon Heavy expendable configuration. This is the variation of Falcon Heavy, where all 3 cores are spent and all of the recovery hardware removed prior to launch. We want to make those stages as light as possible so that we can maximize the lift capacity of the vehicle and ensure that all the fuel on board the launch vehicle is used towards propelling the spacecraft to reach the escape velocity that's needed. I'll point out that during the second stage burn of the second stage, the vehicle with the spacecraft, which is very heavy, will be traveling approximately 25,000 miles per hour, which will be the fastest speed for a Falcon second stage ever. For Europa Clipper, the side boosters that will fly on our mission are pictured there. They flew previously on the Psyche mission, and they're now on their 6th and final flight. All of the other hardware that we're using for our mission is new. In terms of history, the Falcon Heavy configuration has launched 10 times previously, so this will be the 11th, but only the second flight of the expendable configuration. We plan to launch Europa Clipper out of 39A. This is the historic pad where Apollo and shuttle launches occurred many years ago, and it's the same pad where LSP and SpaceX teamed up recently to launch Psyche and the GOES-U mission. Work at the pad is active. The SpaceX team is in the process of converting it from a Falcon 9 to a Falcon Heavy configuration. And I'll say that there's no other launches planned out of this pad prior to Europa Clipper, so we are 100% focused on getting this pad and the vehicle ready. The analyzed launch window for our mission starts on October 10th, 2004, and it has been extended to November 6th, 2024, based on additional performance implemented for the mission. Our original launch date window ended on October 30, but again, we've been able to extend it based on some additional performance that SpaceX was able to squeeze out of the launch vehicle. Those additional days are only for contingency only, and if we need them, they're there for use. In terms of the work ahead, the design of the final trajectory is being optimized as we speak. Space is in the process of getting the final mass property, engine tables, and trying to squeeze as much out of the vehicle as we can. In terms of the hardware that we need to launch Europa Clipper, all of it is here at on site getting processed. The side boosters are going through final refurbishment, and we expect to start booster made at the end of this week. I'll point out that for our mission, there's no requirement for a static fire test. It's being determined not required based on the health of the launch vehicle and the ground system. There's a beautiful picture there of the Falcon Heavy stacked that was taken for Psyche prior to rolling out for their static fire test. We expect to be in a similar configuration to that one here in the beginning of October. In terms of the joint operations, activity are processing on schedule. The hardware that we need to perform that work is all getting cleaned, sampled, and it should be ready next week for start of the joint operations once the spacecraft is fully fueled. We expect to transport the encapsulated assembly from the payload processing facility to 39 approximately 6 days before launch. Once we get there, we'll mate to the front of the rocket, and the spacecraft will do some electrical testing, and it will roll out to the pad approximately 48 hours before launch. Our launch of October 10th is approved by the range, and we also have 2 additional backup days in case those are needed. Europa Clipper will be LSP's 105th launch, and it is my 9th mission as mission manager. But what makes this mission really special to me has been the great team that I've had the opportunity to work over the last 2 years, and more importantly, the science that we're getting out of this mission, which is off the charts. It's one of a kind, and I'm just proud to be part of the team that will get the spacecraft into space and en route to collecting so much amazing science. So I'll summarize and I'll say that we're ready. Activities are progressing on schedule. And with that, I'll turn it over to our next speaker, Stuart Hill.
Hello, everybody. I'm Stuart Hill, and I'm the Product Delivery Manager of the Propulsion Module here at the Johns Hopkins Applied Physics Laboratory. First of all, I just want everybody to know how excited APL and Goddard are to have provided such key pieces of infrastructure for the Europa Clipper mission. It'll enable the spacecraft to do this exciting science mission in and around Jupiter. Our propulsion module is the primary structure of the spacecraft. You can go to my first picture there, is the primary structure of the spacecraft, and you can see a rotating view of our propulsion module, and it's a large cylinder. So you keep hearing the term big or large here about the Europa Clipper spacecraft, and the propulsion module is exactly that. It stands over 10 feet tall and 4.5 feet in diameter, and it provides mounting interfaces for the launch vehicle at its aft end, as well as for the avionics module and the rest of the spacecraft hardware at its top end. The propulsion subsystem is housed within the entirety of the propulsion module structure, and the propulsion module structure is basically sized by the 2 propellant tanks that are within that inner diameter of the cylinder. Those 2 propellant tanks will hold over 6,000 pounds of propellant. As you heard Jordan talk about, that propellant is being loaded inside those propellant tanks as we speak. The propulsion system also consists of 24 engines that will be used for propulsive maneuvers in and around Jupiter, during our cruise to Jupiter, and then once we release from the launch vehicle. Our biggest maneuver is a 6 to 8 hour Jupiter orbit insertion maneuver called JOI for short. During that maneuver, it will be 6 to 8 hours where we will expend 50 to 60% of that 6,000 pounds of propellant. It's hard to believe that this spacecraft is built to carry all that propellant, and it will carry it for 5 years. And then within 6 to 8 hours, it will expel 50% of that propellant in that maneuver. In addition to the propulsion subsystem, the propulsion module is also delivering the solar arrays. If you can go to the next video there, our solar arrays in this video you can see in a time-lapse video are being deployed from the actual Europa Clipper spacecraft down at Kennedy Space Center just a couple weeks ago. Again, these solar arrays are massive, and you can see that large structure around those solar arrays, which are used to offload those arrays because they're so large they cannot support their own weight in Earth's gravity field. That gantry allows the solar arrays to deploy safely and to mimic the deployment that they'll do right after launch vehicle separation. These solar arrays are enormous. You keep hearing large solar arrays here. They are over 45 feet in length, 15 feet in height, and will be used throughout the mission to bring electrical power to the spacecraft subsystems and instruments as we go through our mission and collect the data. In our next picture, if you can go to the next one, we're providing also our RF module or telecom subsystem. Our telecom subsystem is primarily also accommodated on the propulsion module. The telecom subsystem consists of radios, amplifiers, coax cables, waveguide, and switches. There are many antennas spread all over the spacecraft, mostly mounted onto the propulsion module. But the big antenna, the big 10-foot antenna that you see here being installed at Kennedy Space Center, is the high gain antenna, which is a dual band antenna that allows us to get all that exciting science data down to the ground after we get it from the Jupiter system. So when we do our science measurements, we'll be pointed the spacecraft towards the Europa to the moon of Europa, And then once we get out away from this, the moon, we'll be able to turn the spacecraft back towards Earth and use that high gain antenna and get all the data down. So all this infrastructure that we've provided here at APL will be has been tested at Goddard, it's been tested at APL, been tested at JPL, and it's been tested at KSC, and it's ready, or it's nearing being ready for launch. And so for me, what I'm most excited about this mission is, having been on this program for 10 years, we've seen it go from conception to reality. And you know, with children who have grown up in those 10 years, my oldest has almost completed all of his schooling. His father's always worked on Clipper, and my youngest was born a couple months before I started this program. They've only known Clipper, but they've known Clipper in an abstract form. That Dad works on that, but with this launch will make it real. And it's so exciting to be a part of that. And if you fast forward and think about what this spacecraft is going to see and what it's going to send back to us, it's going to be generational. And it's so exciting just to be a part of that and to show everybody what we've been working on for all these years. So with that, I'd like to send it over to our Deputy Project Scientist, Bonnie Barati. Bonnie?
Thanks so much, Stuart. We're pretty certain there's very strong evidence that the ingredients for life exist on Europa, but we have to go there to find out, to make sure that it's really there. Let's look at the first image. Okay, this is a picture of Europa that was obtained by the Galileo spacecraft, and we see there are bright icy plains, intriguing cracks, and many interesting features, but perhaps the most important thing is that there are very few craters, signaling that there's some type of either active geology or recent geology. We do know quite a bit about Europa from previous missions. The first close-ups we got from Voyager 1 and 2, which went by in 1979. And the Galileo spacecraft, not the man, Galileo discovered Europa in 1610. The spacecraft Galileo made 12 flybys, close flybys of Europa. And perhaps the most important finding was that there is almost certainly a global ocean. So let's look at the next image. This is a close-up from the Galileo spacecraft. And here you can see this is in the region known as the chaos terrain. There are very few craters, just a few. There are these intriguing cracks and these unusual features that may give evidence for interactions with the global ocean down below. So the three things we need for life, for a habitable environment, now just to emphasize, we're not a life detection mission, we're just looking for the conditions for life, is water, some type of chemicals, specifically organic compounds that can serve as food for any primitive organisms, and then finally, energy. So let's just look at this cutaway model. This is the interior, the upper part of the interior of Europa. And first of all, we have this ice crust. We're not certain how it interacts with this global ocean down below. That's one of the things we're going to go there to find out. We're not sure whether water seeps into the ice crust and forms pockets, whether it comes to the surface. But let's go down here to the interface between the upper rocky mantle and this global ocean. One of the things is to find out what that interaction is. Does it put salt into this ocean? But the most important thing, I think the most intriguing thing, is there has to be a source of energy on Europa in order to provide a habitable environment. There's only about 4% of the solar radiation that comes to Jupiter, that is Europa, from the sun compared to the Earth. But there's another form of energy. Jupiter is huge. It can contain about 1,000 Earths. So it has a lot of gravity. The orbit of Europa around Jupiter, about 3.5 days. When it's close to Jupiter, it's not quite circular. So when it's close, it gets kind of squished in due to this gravity, and then when it's far away, it kind of flexes out. So this flexing in and out produces heat. That's the source of energy that we have. In fact, we see over there on the far side of this cutaway, there are these intriguing thermal vents that not only are hot, but have this heat liberates chemical energy. And this is what we believe is the source of energy on Europa. And they may be similar to thermal vents in the deep oceans of the Earth, where primitive life exists and where life may have originated on the Earth. So that's what we're going to find out from Europa Clipper when we get there. So let's see. Let's look at the final image here, the video of the spacecraft and the instruments. Yes, what are these instruments going to do? What are the instruments? This is the biggest spacecraft ever sent into outer space with the most sophisticated instruments. Starting in the ultraviolet part of the spectrum, our eyes can't see that. We have UVS to study the surface and the atmosphere. Then we have ICE, which is the cameras. There's a wide angle and a narrow angle camera to take impressive pictures, images down to 1 meter resolution. Then we have a infrared spectrometer to look for the fingerprints of the chemicals, especially organic molecules we're looking for. Then a thermal infrared mapper that will look for hot spots and understand the texture of the surface. And then there's also an ice penetrating radar, which is going to study this crust, the upper part of the crust and parts of the ocean. There's also 4 fields and particles experiments. There's a magnetometer, which will study the interior, especially the ocean, try to understand what that is like. There's a plasma detector, which will look at these highly energetic particles around in the environment of Europa. Then there's also a dust detector, and then an instrument, mass specs, which will look for these sophisticated organic molecules that could provide the food for if there are any primitive organisms. So those are the main instruments on board. As I said, they really are the most sophisticated suite of instruments on the largest spacecraft. So there will be 49 flybys of Europa to study the moon from pole to pole. We have pretty much complete coverage, and it will not only realize the main goal of this mission, which is to search for a habitable environment where possibly life could thrive, but it will also address the 3 major objectives of understanding the geology of the surface, the composition, and then to characterize the interior. So people ask me quite frequently, well, what is the thing that most interests you? Every mission we've ever been to, we have always uncovered things that we could not have imagined. That is the thing that really most interests me. There's going to be something there, the unknown, that is going to be so wonderful that we can't conceive of it right now. That's the thing that excites me most. Thank you. Back to Shahre.
Okay. All right. Thank you, Dr. Barati. We're ready to take your questions now. So for media on the telecon line, press *1 and direct your question to a panelist. If you're on social media, you can use the hashtag #AskNASA, and we may have some questions in the room, so just raise your hand. So we're going to start with the phone lines. So first we've got Eric Berger from Ars Technica. Go ahead.
Hi, thanks very much for doing this. A couple questions. First of all, I think maybe for Jordan Evans, are you targeting the top of the launch window on October 10th, or are there some schedule slips that may push a little bit later into the window? And second, y'all have been very careful to say multiple times that Clipper is not a life detection mission. However, what are some things that you might observe that would be suggestive of potential life in the oceans below? Thanks.
Thank you. I'll take the first one. So we are absolutely targeting the first day of the launch period, October 10th. It's an instantaneous launch window with each day. As Armando mentioned, the range is set for the 10th through the 12th, but we are on track for the opening of the launch period on October 10th.
Bonnie, you want to try the second?
Yeah, I mean, if there is life on Europa in this habitable environment that we're exploring, it will be underneath the ocean, so we wouldn't be able to see it. We're looking for chemicals on the surface, organic chemicals that are the precursors to life. There are, dream things we could observe, like DNA or RNA, but we don't expect to see those. So it really is just looking for a habitable environment and evidence for the ingredients of life, not life itself.
Armando, was there anything else you wanted to add about the opening of the launch period?
No, like Jordan mentioned, we are tracking right on schedule. Our schedule has a margin to the 10th, and I feel pretty confident that unless something unusual comes up, they'll be ready to launch on the beginning of the window.
Okay, great. We're going to take another phone call, and then we'll come to you in the room. Alexandra Whitsey from Nature Magazine. Go ahead.
Yeah, hi. Thanks for taking my call. This is for Bonnie Barati. could you talk a little bit about kind of the cadence of discovery? So sort of once you're at the Jupiter system and starting to do those flybys, do we sort of expect to get a lot of answers to those big questions you're looking for, those big science questions, on like flyby 1, or is it going to take to flyby 5? Like, how quickly will we get those, first glimpse at these big questions we're looking to answer?
Yeah, thanks for that question. That's a great question. It's really exciting, and also, I actually did my PhD thesis on the Voyager spacecraft, so I've kind of seen the way this is unfolded, and it's unfolded slowly. I mean, prior to Voyager, we didn't even know that the surface was weird like this. So there's going to be immediate fast things. We'll be able to tell right away, to confirm the discovery of Galileo, whether or not there is a global ocean there. Just by the way the spacecraft goes by, if it sloshes, the spacecraft orbit is going to be different than if it's a totally solid body. So we will know that right away. The second thing that will hit us, is the surface. The cameras on board Europa Clipper are far better than the ones on Galileo. So we'll be able to see these close-ups to see what is the surface like? Are there plume deposits? What do these cracks really look like? So I would say within the first few flybys, we'll just have an onslaught, a deluge of scientific data. And then the stuff that comes later will be more looking at the details of, how deep is the ocean, how thick is the ice crust, what are the interactions between the ocean and the crust. So a big deluge, and then adding on to that, I think will be the cadence.
Okay, we're going to come to the room and go ahead and introduce yourself.
I'm Emily Lakdawala for Sky and Telescope. I have a lot of questions, but I'll confine myself to two. The first one is just a launch day question. If the launch is scrubbed for weather or whatever reason, do you have another launch opportunity that day, or does it need to be recycled to a subsequent day? And the second question is for Bonnie. We know that there are almost certainly the habitable environment ingredients at Europa. So can you be a little more specific about the particular discoveries you expect to make that will help you characterize that habitable environment a little bit more?
Okay, well, maybe we'll start with Armando for that reset question.
So yes, so it's a single opportunity per day. So if we scrub before the launch vehicle is fueled, we have an opportunity the next day to attempt again. If for some reason we fuel the launch vehicle and we scrub, we have to wait 48 hours for the next opportunity.
Okay, the most important thing for determining whether there's a habitable environment and life there, I really think that would be the compounds at the surface. The ocean is still going to be, since it's so far below the surface, it's still going to be somewhat vague, but we can see the surface with the spacecraft, the infrared spectrometer for Europa. We'll be able to see, first of all, the connections between the ocean and the surface. Are we going to see things like evidence for evaporation, evaporate deposits at the surface? What kinds of organic compounds are we going to see? Are there going to be the sophisticated carbon compounds that are the building blocks of life? Will we see, for example, polycyclic aromatic hydrocarbons? The dream thing, which we don't expect, but will we see a simple amino acid? Those are the things that I think would be the big steps forward.
Okay, we're going to go back to the phone lines. We've got Irene Klotz of Aviation Week.
Thanks very much. I have a question for Armando first, which is you mentioned that the launch window was able to be extended about a week or so based on Falcon Heavy performance. Did SpaceX actually do something to enhance performance, or was this based on a reanalysis? And I have a question also for a science question. Thanks.
Armando, why don't you go ahead and answer this one, and we'll come back to you, Irene. Oh, okay. Well, let's take the science question first, actually. Irene, why don't you come back and ask? I'm sorry, we're having a little technical difficulty here.
D'Abbraccio, in your opening comments, you said that this was the first in-depth mission to characterize habitability, and I don't mean to pick apart your comment, but that's kind of the mantra of the first Mars rover Curiosity mission. So I'm wondering if you might be able to take a stab at how you look at this Europa Clipper mission compared to the extensive life habitability questions that had been addressed in the Mars program. Thanks.
Absolutely. So our Mars program is very robust, as you know, and we have been searching for habitability and life for quite some time now. With Mars, it is easier to explore for the sense that it's closer to Earth. We have ground-based observations, and there's a lot of ways to do it. And I will turn this over to Lori in just a second so she can talk a little more about the Curiosity rover and the science that it's doing. But from this perspective, Europa is so far away, and all of the other bodies are in terms of habitability, that this is the first time that we really have a mission that's specifically dedicated to looking for habitability. Some of the science goals of Curiosity really are dedicated to that, but that's not the only goal of the mission as it is with Clipper. Lori, would you like to add to that?
Sure. Thanks, Gina. I think it's actually a great question. I like to talk about the fact that we're kind of in a space race with ourselves when it comes to thinking about looking for life, right? We're thinking about habitable environments on Mars. We're thinking about them on Europa. We're thinking about them on extrasolar planets, where we're also trying to get to the point where we're analyzing the photons directly from those extrasolar planets so that we can ask questions about their habitability. To me, this is an exciting foundational underpinning of NASA's space science program right now. So much of it is about life in the universe. On Mars, we're looking for ancient life because we know the environment there was much more habitable, more liquid water around very early in Mars history. And of course, it actually preserves the time in planetary evolution, the first billion years of planetary evolution, which is very hard to explore even here on Earth. We've got that on Mars. Europa, the excitement is about a current habitable environment, right? A current ocean. There is an ocean there today. So it's different, but very complementary. And about this foundational question of, are we alone in the universe?
All right, thank you, Dr. Leshin. Armando, do you want to take a stab at that question about how the launch period got extended?
Oh, sure. So the launch period got extended based on a combination of factors. Basically, SpaceX was able to get more performance out of their launch vehicle based on some hardware modifications that enable the launch vehicle to utilize all the fuel in the boosters. I can't get into the specifics because of proprietary nature. The other factor is this is SpaceX's 11th flight of the Falcon Heavy configuration. They've flown it a few times already, so they come up with a strategy to optimize the throttling of the launch vehicle to get the most performance out of it. And the final thing is typically we need ground assets to get telemetry from the launch vehicle. And those ground assets are typically not in the most ideal locations. So we have to tweak the trajectory to ensure that you're over a ground asset before you do your burns. And for this mission, we are relying on TDRS for the launch vehicle telemetry, and that gave us a lot of additional performance as well. So it's a combination of factors that allowed us to extend it from the 30 to November 6th.
Okay, thank you, Armando. We've got another call on the phone lines. Marcia Dunn from the AP.
Oh, yes. Hi, Marcia Dunn, Associated Press, with a few questions. What is scientists' best guess on how deep this ocean might be, and if there is or was life? Do scientists believe it's microscopic? Could it be bigger, minnow-sized? Just trying to get a handle on what kind of thoughts are going into the life question. And lastly, what happens to Clipper at mission's end? Thank you.
Okay. Yeah, the first question is, we don't know exactly how deep it is. That's one of the things we're going there to find out. Probably from the top around 60 to 80 miles. And the type of life there, we expect, again, Europa Clipper is not a life detection mission, but using an analogy to Earth, which may be dangerous, the types of life that originated in these deep oceanic vents were primitive. They're primitive bacteria, even bacteria that don't need oxygen in their metabolism. So we would expect there to be, if there's anything there, it would probably be primitive. But again, we don't know. We will not know from this mission because we can't see that deep.
Yeah.
So end of mission disposal is planned at Ganymede. So once we are finished with the science mission and NASA has determined that we need to properly dispose of the vehicle so that we don't run the risk of impacting Europa at some future date, we do a series of burns that impact Ganymede directly. And that's our chosen disposal target and approved by the Planetary Protection Officer of NASA.
Great. Okay, we're going to take another call from the phone lines. Bill Harwood from CBS News.
Hey, thanks very much. I think this is for Mani Barati. If the crust is 60 to 80 miles thick, something like that, will the flybys alone pin that down and help you nail down how thick the crust is, or are other instruments going to help you do that? And how does the radar play into this? I mean, how deep can it penetrate theoretically? And finally, I'm sorry to ask three questions, but finally, as you fly by and this thing's sloshing around and you're measuring changes in your trajectory to figure the ocean scenario out, I mean, what are we talking about in terms of how much this changes the trajectory? I mean, I think the average person would be stunned that you can do that. And I'm just trying to figure out a way to kind of explain the subtleties involved in how you come up with, the nature of that ocean based on the changes to the trajectory. Thanks.
Yeah, okay, thanks so much. Great question. So first of all, the crust itself is only, we're going there to find out, but it's more like 10, 15, 20 miles thick. The ocean is as you could see from the cutaway, is actually much deeper. The ice-penetrating radar, which is similar to ones we've used on the Earth and also on Mars. There are two instruments in orbit around Mars now. It has two frequencies, and it is going to send these long wavelength electromagnetic waves through the surface. That's the trick. It can see through the surface, and we hope that it can see down to the interface between the crust and the ocean. It's TBD, it depends on how deep it is, but we hope that it can see down that deep. But it definitely can probe whether or not there are any little ponds or lake-type features within the crust. That's not so deep, so it will be able to see that. Let's see, oh yeah, the sloshing. Okay, so our instrument, we have a navigation team here that can really track the position of the spacecraft within meters and in some cases within centimeters. So the pull of the ocean on that spacecraft really varies according to how thick it is, how dense it is, what the composition is, and the navigation team will be able to track all those changes and understand the nature of the ocean. And the instruments that will be doing that, first of all, there's a magnetometer. The characteristics of the ocean are also told in its magnetic field. So this induced magnetic field that Europa has, the magnetometer will be tracking that, and the gravity experiment on board the space. There's kind of an additional experiment, which I think I neglected to mention. There's a gravity experiment that just uses the antennas to track the position of the spacecraft, and that does depend on the depth and the nature of the ocean. And again, the gravity experiment tracks it to within meters and in some cases centimeters. So we will be able to tell a lot about the ocean from both the gravity experiment and the magnetometer.
Did we get all your questions, Bill?
Yeah, that's fine. Thank you very much.
All right, great. All right, we're going to go to social media. We have this is a question for Stuart. Ticker on YouTube asks, why not use RTGs instead of solar panels? Wouldn't that reduce the size of the spacecraft?
It's a great question. Yes, it would, but the policy of the United States government is to fly solar if you're able to fly solar. So originally, the spacecraft back in 2014 did incorporate RTGs. We made the decision at the turn of 2014 and 2015 to translate to solar arrays. It's been interesting to watch how those solar arrays have grown over time. The original concept of those arrays had 3 panels. You'll notice ours now have 5. But that is how we got to solar arrays, and I think we've made a great decision.
Great. Okay, I got a question for Dr. DiBraccio. Safir Jamil on YouTube asks, how is the collaboration with ESA's JUICE mission for joint observations coming along?
Oh, that's great. So JUICE is currently on its way to Jupiter to explore the icy moons there as well. And with NASA, we do have some contributions. We've actually contributed to a few instruments on JUICE. Right now, the science teams are collaborating and planning for further collaborations once both of the spacecraft are in orbit at Jupiter. And so we look forward to the exciting results that will come out of both of these missions as they're at Jupiter at the same time.
Great, thanks. Okay, we're going to come back to the room. Go ahead.
Hi, Emily Lochtawala again. For Bonnie, I'm wondering, Voyager had 2 flybys, Galileo just had a few. This mission will have 49. Will the longevity of the mission enable you to do some of the things that you can have done with long missions on Mars, things like change detection or opportunistic observations of other moons? Will you be able to do those kinds of things planned in the primary mission? And then I have a question for Gina, which is that you've mentioned that we have explored the gas giants and now we're returning to one of the moons. We haven't really explored the ice giants, and I'm wondering if NASA is pushing forward on a Uranus or Neptune mission in the future.
Okay, start with
Okay, yeah, all of the above, all the things you mentioned. I mean, we will be able to look for change. Another thing we'll be able to look for is active geology, not just on the surface, but if there are any plumes there, for example. There are some putative observations of plumes from the Earth, so we'll be looking for that. And in terms of exploring other objects, we are going to be going by Ganymede and Callisto. There are no plans right now, basically for budgetary reasons, to observe these moons. But if any past missions are the guide, we'll probably be doing something when we're there, maybe for free, but we'll look. Yeah.
Dr. DiBraccio, you want to address the other ones?
Sure. Yeah, so to answer the second question there, first let me say, even though we have explored the gas giants and the terrestrial planets, there are still many outstanding questions about all of the planets that we would love to answer. Now, in terms of the ice giants, the only in situ data that we have so far are from the Voyager flybys that took place in the late 80s. And so in our recent decadal survey, the Origins, Worlds, and Life that came out, that sets really the community recommendations of planetary science over the next decade, a Uranus orbiter probe mission was listed as one of those high priority missions for the future. Now, that's something that we are definitely excited about at NASA and something that I know the community is really pushing forward to. There's been a lot of community workshops and it is on our radar. But right now, our first priority is to get Clipper off the launch pad and to Europa.
Okay, thank you very much. We're going to go back to the phone lines, and we've got Nadia Drake from Scientific American.
Hi, and thank you for taking my question. I think early on we heard that scientists think ocean worlds like Europa might be a common type of world outside our solar system. And I'm wondering, what is the scientific reasoning behind that idea? Have we detected another such ocean world, or is this idea based on extrapolations from our own solar system, or based on modeling of exoplanetary systems? Where does that idea come from?
I think, Dr. DiBraccio, you brought that up in your opening remarks. Do you want to take that one?
Can we repeat that question?
Go ahead, Nadia.
Sure. Yeah, I was asking about the idea that ocean worlds like Europa might be a common type of world outside of our solar system. And I'm wondering what the scientific reasoning is for that idea. How do we get there? What are the data? Can you walk me through it?
So I actually am not the expert on that, and I'm curious if Bonnie has anything to add to it.
Yeah, I think it's basically exoplanets. The ocean worlds tend to be much more prominent and also ice giants tend to be much more prominent in the exoplanets. And it's basically looking at their mass and their density, which you can get from, basic astronomical observations and using the models that we have on Earth and extrapolating to what the interiors look like. And it turns out that a lot of these bodies are ocean worlds or ice giants, which is in our own solar system is Uranus and Neptune.
Okay, thank you, Bonnie. Next question is from Jim Siegel of Florida Media Now.
Hi, everybody, and thank you for taking my question. This is certainly an exciting mission, and I don't mean to be flippant about this, but suppose you do find strong indications of conditions that would support life. So what? I mean, what's the next step? Is there a next step? Thank you.
Gina, that's you.
Yes. Dr. DiBraccio.
Well, let's discuss the priorities, right? So right now we're searching for whether Europa is habitable or not. Depending on what we see, we might choose to send a mission to go back to actually determine if life currently exists. Now, as I mentioned, with the way that our priorities are set, many of these big missions are really based on the survey, the decadal survey recommendations, and what the community recommendations are. So once we get the results from Clipper, we turn it to the community to see if we feel like that would be a priority for the next steps. So, we really look for input to the greater science community to see, so what, do we care? Do we want more of that data to really answer the next questions?
Okay, thank you. We're going to go back to social media. This will be a question for Jordan. DP Patel on Instagram asks, how will you protect the moon from possible microbes on the spacecraft?
That's a great question. So planetary protection is the discipline that we have that looks at trying to ensure that we are protecting the moon, our scientific target, from bringing microbes with us. And so all of the hardware goes through an extensive program of decontamination, we'll call it, things like dry heat microbial reduction and cleaning with hydrogen peroxide vapors to try to get us to a level of cleanliness that ensures that we are statistically protecting the moon from any microbes that might have been present on board the spacecraft. So there's a lab set up at Kennedy Space Center where we're regularly taking samples of the spacecraft and trying to grow spores and see that we are maintaining that cleanliness that we had early on in the development of the hardware.
Great, thank you. This is, I think, maybe a question for Bonnie. Cello Fingers on YouTube asks, is Clipper more advanced than Cassini in its camera and spectral equipment?
Yes, it is. The spectrometer is more highly resolved. It's more flexible. It has a scanning mirror. It can look over larger areas. Resolution's better. The camera is it's actually more innovative. It has a wide-angle camera of about, I think, 45 degrees. There are two cameras, a narrow and a wide angle. So it's just more flexible. It also has a gimbal that it can move. So we'll be able to see a lot more and detect a lot more with these instruments.
Okay. We've got some more folks lining up on the phone lines. Again, if you guys want to keep asking questions, it's *1 on the telecon line. All right, we've got a follow-up from Irene Klotz of Aviation Week.
Thank you. I was just wondering if, following the most recent assessment of the transistors from radiation exposure, concluded that there is any greater risk of the transistors failing earlier than previously planned, or did the analysis just basically completely reset the clock to what it was as far as mission risks? Thanks.
Can we take that one?
Yes,
sure.
Jordan.
So as far as mission risks, we determined that flying with these transistors that do degrade earlier than they were originally qualified for don't present an appreciable mission risk for Europa Clipper. It is low risk to fly these transistors, not only through the primary mission, but at the end of that primary mission, looking circuit by circuit to ensure that we had sufficient margin in each of the circuits. The robustness of the design allowed us to accommodate these transistors and ensure that we had appropriate margin at the end of the mission.
Great. Okay. Next call is from Leo Enright of Irish Television.
Thanks, Jairi. I was really intrigued by this spacecraft disposal plan at Ganymede. I don't remember hearing this before, so I was wondering, is it new? And secondly, obviously Europe will be putting a spacecraft in orbit around Ganymede, so is there a possibility that the JUICE mission could actually image the impact of the Clipper at Ganymede? I also had a launch window question, if possible.
Okay, well, we'll take the disposal question first. Go
yeah,
ahead.
So the original plan was to dispose of Europa Clipper at Jupiter, and I think it was about 2 years ago that we received approval from the Planetary Protection Officer to make Ganymede the disposal target. It requires less fuel. It's a more elegant solution at the end of mission, and a lot of things can happen between now and the end of Europa Clipper's mission in terms of whether JUICE was able to image, but that would certainly be a possibility.
Go ahead with your follow-up, Leo.
That's pretty exciting. Thanks for that information. Yeah, I was just wondering about launching late in the launch window, say in November, and this again in a way relates to JUICE. Would that change your arrival date? Would you end up arriving maybe after JUICE or something?
All of the launch opportunities that we have in this 4-week period end up with the same arrival in April of 2030. So no, it would not change our arrival at Jupiter.
Okay, thank you. Next we have another call. Marcia Smith, Space Policy Online.
Thanks so much for taking my question. I'm wondering if you did decide to send a lander based on the information that you get from this mission, what do you need to know about the surface of Europa, and will this mission tell you what you need to know so that you're prepared if you eventually got a permission to send a lander there?
I think Dr. DiBraccio, do you want to take that one?
Well, I'm actually looking at Bonnie in terms of talking about the images that we're taking on the surface and how that would inform the measurements we would want to follow up on.
Yeah, a lander is really a question of risk. You have to have a surface where the landing vehicle is going to survive. So you can't have, for example, an area that has a lot of blocks or is all fluff or something like that. So yes, we will be able to determine those things from orbit. The camera, not only the camera, but the infrared spectrometer, the one that sees the heat, will be able to look at how fluffy the surface is and the block size. So yes, we will be able to map out Europa for appropriate landing sites.
Okay, I'm going to take one more social media question also on this idea of what if we are able to extend. At Chris Broad on X asks, NASA's uncrewed missions have a good track record of operating long past their projected mission end date. So what mission objectives that are not a priority for the initial timeline are being considered in the event of an extension? Who wants to take that one?
Well, I'll jump in.
Okay, there we go.
On this one.
Go ahead.
And say, right now our team has been focused on setting these primary objectives and the goals that they will achieve and making sure that we can get there safely to achieve those goals. So just as part of our extended mission process, when the time comes, the science team will be working really hard to develop those goals, but it's a little premature at this point. We need to see what we're observing first to know what we might want to do in the future.
Okay, all right. Thank you, Dr. DiBraccio. For media who want to get a deeper dive, we do have our press kit now available. It's go.nasa.gov/Europa Clipper press kit. We also have a number of ways for you to keep up with the Europa Clipper mission. If you want to look on the web, we've got go.nasa.gov/Europa Clipper. We also have a number of social media accounts. You can follow Europa Clipper on X and Facebook, and NASA JPL, NASA Solar System, and NASA on Instagram. There are also a number of ways that you at home can participate in the Europa Clipper mission. Visit go.nasa.gov/Europa Clipper participate. There's some kids art challenges, virtual guest events, and more. We do also have some additional live events coming up in the weeks leading to launch. If you go to the NASA YouTube channel, you can set a reminder for our live launch commentary show. And if you want to see the variety of platforms where we're going to have our live events and a schedule of when those events are, you can go to our Watch Online page. All right, we are also going to drop these links in the chats because I know that we have a lot of them here. So thank you very much for joining us, and go Europa Clipper.